Hey guys, welcome back to a new video. This session will be the first one in our series on combinatorics and probability theory. Now, because these topics are oftentimes experienced as very difficult and confusing to a lot of students, I decided to make several videos on it, starting from the basic exercises and working our way up from there. Now, particularly for these topics, it is very important to make plenty of exercises in order to get a feeling of how to solve such problems. It is simply not enough to learn and understand the theory. As always, the timestamps of each exercise can be found in the comment section below. And if you enjoy these videos, consider giving them a thumbs up, which helps out tremendously. And with that, let's get into the first exercise. In this first exercise, we are going to be counting the number of matches in your typical tournament. For example, the World Soccer Championships. These tournaments are oftentimes structured in a similar fashion, and they proceed in several phases. First, you have the group stage, then you have the round of 16, the quarterfinals, the semifinals, and eventually the final match between two teams that will determine who is the winner. Let's now in this exercise consider the case where we start out with 32 teams competing to become the winner. These teams are divided into 8 groups and each group consists of 4 teams, because 4 teams times 8 groups equals our 32 teams. And the question that we will solve in this exercise is, given that we start with 32 teams and these 5 stages of our tournament, what are the total number of matches played in this entire tournament from group stage to final? And to do this, let's of course first start with our group stage. And the group stage will work as follows. Within each group of 4 teams, each team will have to play each other team. And the 2 teams that won the most matches within each group will advance to the round of 16. Now the question in this group stage is of course, how many matches within each group will be played if these 4 teams will each have to play each other team? Let's take for instance the example of group 1, and then we can simply generalize this to all of the 8 groups. The first thing that we need to realize is that a match consists of 2 teams playing against each other. This means that we can denote a single match as a pair of 2 numbers. And these 2 numbers are then of course either team 1, team 2, team 3 or team 4, each of the 4 teams within this group. For example, if team 1 and team 3 play each other, then this can be denoted as T1 and T3, the pair of numbers T1 and T3, which signifies the match between these 2 teams. This notation allows us to rephrase the question of how many matches will be played to how many pairs of 2 numbers can we make out of these 4 numbers. Well, let's say that we indeed have to compose a single pair. For the first position here, in this pair of numbers, we have of course 4 choices. We can either put T1, T2, T3 or T4 in this position. Now, how many choices will we have left for the second position? Well, this actually will be 3 choices. Now, why exactly do we only have 3 choices for the second spot and not 4? Well, let's say that for the first spot, we took team 1. And this means that for the second spot, we only have T2, T3 and T4 left. Because of course we cannot choose T1 again, because that would mean that we have T1, T1, and this would be a match of team 1 against itself, which of course is not possible. Therefore, we only have 3 choices left here. Let's say for instance, team 3. Now what is the total number of choices that we had in making this entire pair? Well, we simply multiply the number of choices of position 1 with the number of choices of position 2. And this results in 12 possible choices that we could have made in making these pairs of teams. However, as you have probably noticed already, there is another pair of 2 numbers that is actually equal to the pair of numbers that we already have here, T1 and T3. Let's now say that for the first position, we have T3, and for the second position, we have T1. Now we see that this is of course the same match as before, as T1, T3. It is basically team 3 playing against team 1. However, this pair of 2 numbers is also contained in these 12 choices. So clearly, the match between team 1 and team 3 we counted twice. And this will be the case for any choice that we made of 2 teams. Each time we counted the match twice. To account for this, we need to divide the number of choices that we could make by 2. And doing this, we see that the total number of matches within each group of 4 teams is 6. Now, of course, because we know that there are 8 groups, and we know that for each group we have 6 possible choices that we can make, so 6 possible matches, we know that in the group phase, the total number of matches is 8 times 6, or it is equal to 48. So in this first group phase, there will be 48 matches. Now, as I said, for each group, the 2 best teams, so the teams that won the most, will advance to the next round, the round of 16. This means that our total team player base reduced from 32 to 16 teams. So at this point, in the round of 16, obviously, we have 16 teams. So what is the number of matches in the round of 16? And to figure this out, it is important that from the round of 16 and on, each team will only play one other team. And therefore, since a single match consists out of 2 teams playing against each other, if we have 16 teams left, this means that there will be 8 matches in total for the round of 16. The winning team of each of these 8 matches in the round of 16 will advance to the next round, which is the quarterfinals. This means, of course, that the number of teams in the round of 16, which were 16 teams, got reduced to 8 teams because only the winning team for each match advanced to the quarterfinals. Now again, in the quarterfinals, each team only plays one other team. Since a match consists out of 2 teams playing against each other, 8 teams means that there are indeed 4 matches, 4 quarterfinals. And of course, the winners of these 4 matches will advance to the semifinals. This means that the number of teams will reduce again from 8 to 4, and each team will again play one other team, meaning that in this case there will be 2 matches, 2 semifinals. And of course, these 2 matches determine who will get to play the final. Therefore, we know that our teams will have reduced from 4 to 2, and 2 teams, of course, make 1 match. So we have 1 final who will determine the winner of the tournament. So let's now go back to the initial question that we had. What is the total number of matches played in this tournament? Well, at this point, we can simply add all of the number of matches for each round together to obtain the result. So we had 48 matches in the group stage, we had 8 matches in the round of 16, we had 4 quarterfinals, 2 semifinals, and of course 1 final. And this gives us a grand total of 63 matches played in total in this tournament. And before we go to the second exercise, let's compare this result with the scenario where each team would play each other team. So the scenario where there weren't any rounds, but simply one big round, and then the team that won the most matches will win the tournament. So how many matches will be played in this scenario? Again, let's denote a match as a pair of 2 numbers. And these numbers, of course, represent the teams from T1 to T2 all the way to Team 32. So how many pairs of these numbers can we now form with these 32 numbers? Well, again, as we did before, on the first position, we have 32 choices because we can choose any team from all of the 32 teams. Let's say, for example, T12. Now, how many choices do we still have for the second position? Well, this will be 1 less, so 32 minus 1, because we cannot choose T12 again. So this will be 31 choices. So if we now multiply these 2 choices together and we divide them by 2, because we need to take into account that we can swap these 2 positions around, because we would count them twice, which gives us a grand total of 496 matches, which is significantly more than the 63 that we had in the previous case. In the second exercise, we are going to be coloring flags, and more specifically, flags that consist out of 3 vertical bands, which is the case for many countries here in the European Union. Yes, we have boring flags. And the question here is quite straightforward. Let's say that we have such a boring flag consisting out of 3 vertical bands, but it doesn't have colors yet. Let's say that you have 3 colors to your disposal. Let's say blue, green, and red. In the first scenario, we will look at a case where no 2 colors can be the same. This means that each color, blue, green, or red, can only appear once in our flag. So how many flags can we make with these constraints? And as we did in the previous exercise, the first step of solving such combinatorics problems is to try and write our problem in a more mathematical way. Here, for instance, we can associate each vertical band with a place in a triple of numbers. And in this case, the numbers will simply represent the colors. So we again reduce our problem to finding the number of combinations that we can distribute 3 numbers over 3 positions. For the first position, we evidently have 3 choices. We can either pick blue, we can pick green, or we can pick red. And because no color can appear twice, we see that for the second position, we only have 2 colors left to pick from. Let's say that in the first case, we choose blue. This means that in the second case, we can only choose either red or green. Let's say, for instance, green. And this directly gives us the result for our last place, which we only have 1 choice left, which is then of course the color that remains, which is 3. So this means that the total number of choices that we had to color this flag was 3 times 2 times 1, simply the product of all of the choices for each individual band. And this comes out to be 6. So we have 6 different flags using the colors blue, green and red, if no color can appear twice. Now this was straightforward enough, and you could have easily drawn all of the combinations possible, so you didn't have to do any mathematics, simply drawing all of the combinations and adding them all up. However, this brute force method of simply drawing all of the combinations becomes infeasible when the number of colors increases. So let's say that we now have 4 colors with which we can color our flag. Let's say that we have blue, we have green, we have red, and of course now we have also yellow to color our flag. And again, we have the constraint that no color can appear twice. So let's again draw our empty flag, which can be represented by a triple of numbers, or a triple of colors in this case. Now in the first position, we have 4 choices of colors. We have either blue, yellow, green, or red. Let's take, for instance, blue again to be the first color. This means that in the second position, we still have 3 choices left. We have green, yellow, and red left to pick from, because blue cannot be picked since it already sits at the first position. Let's say that for the second choice, we take the color yellow. This means that for the last position, we have 2 colors left to pick from, either red or green. And let's pick green for this example. This means that in this case, if we have 4 colors, the number of possible flags that we have is again multiplying all of the choices together, which becomes 24. So we have 24 possible flags that are distinct and have a different combinations of colors if no color can appear twice. And we see that 24 is already a large number to be brute force drawing all of the possible combinations by hand. Let's now go to the third scenario, where we show that you oftentimes cannot fall back to a brute force method of simply drawing all of the combinations, because drawing 24 combinations might still be manageable when your life depends on it or during an exam. However, in combinatorics, when numbers get even a little bit large, for example for 10 colors, we will see that this simply would not be feasible, because numbers explode quite fast. Let's say that you have 10 colors. And we again draw our empty flag that we need to color with 10 colors without the same color appearing twice. Again, we see that this is a triplet of numbers or a triplet of colors. For the first position, in this case, we have 10 possible colors to choose from. This means that for the second position, we only have 9 colors to pick from left, because we cannot choose the color that we chose for the first position. Therefore, 10 minus 1 colors. For the third position, we have 8 colors left, because we cannot pick one of the 2 colors that we picked in the first 2 places. Therefore, multiplying these number of choices together, we get a total of 720 possible choices to color this 3-colored flag if we have 10 colors available. And to show how fast these number of choices explode, let's for example take that you have 25 colors to pick from in order to again fill our flag with 3 vertical bands. So let's again consider our 3 vertical band flag, which we can now color using 25 colors. Again, this is represented by a triplet of colors, for which on the first position we have 25 possible choices. For the second position, we have 24 choices. And for the third position, we have 23 choices. Now, if we multiply these number of choices together, we get an even bigger number. And even though our number of colors increased by a factor of 2.5, we will see that our number of choices will actually increase much, much larger. In this case, we will have 13,800 possible flags that we can make. So this is an almost 20x increase from our previous case where we only had 10 colors. Let's now go to the third and final exercise where we will look at a bit more complex and involved situation. We're going to look at the number of possible combinations when playing the lottery. Let's first define the rules. Here in Belgium, you're allowed to pick 7 numbers, and each number can range between 1 and 45, and you cannot choose the same number twice. So a possible example would be, for instance, 2, 5, 11, 43, 10, 8, and 20. What's also important to note is that the order of these numbers does not matter. For instance, if I swap this 2 and this 5, this will still be the same combination. So the first step to calculating the number of possible combinations, we again translate the problem to a more mathematical form. In this case, we have 7 numbers to pick from, which can be denoted as this list of 7 numbers. And again, we're going to look at each position, how many choices we can make. So let's see. In the first position, we still have any number that we can pick. So we have 45 choices to pick any number. Then in the second place, we still have 44 choices left because we cannot choose the same number twice. If we picked a 1 on the first spot, then we simply cannot pick a 1 on the second spot. Therefore, it has to be, for example, a 5. And this means, of course, that for the third spot, we have 43 choices left. For the fourth spot, we have 42 choices left. Fifth spot, 41. Sixth spot, 40. And eventually, on the seventh spot, we have 39 choices left. As we did in the previous exercises, the total number of choices is multiplying all of the number of choices for each spot in this list. This means that we need to multiply 45 with 44, multiplied with 43, all the way down to 39. And at this point, it is worth introducing the factorial notation, which is a notation that is oftentimes used in combinatoric exercises. And let me introduce it with an example. Let's say that you multiply 5 by 4 times 3 times 2 times 1. So all the way from 5 to 1. We can write this as 5 factorial with this exclamation mark. And this basically says that this number in front of the exclamation mark, 5, we multiply with all of the numbers all the way to 1. However, this also means that if we have 5 times 4, that we can write this as 5 times 4 multiplied by 3 times 2 times 1. But because we multiply with 3 times 2 times 1, and it wasn't there in the first place, we need to divide it away again. And we see that if we cancel these two terms out, we indeed get this 5 times 4 again. However, we see that we've rewritten this 5 times 4 now as 5 factorial in the enumerator, from 5 all the way to 1, divided by 3 factorial in the denominator, 3 times 2 times 1. And this is how this notation works. And we see that we can apply this with our multiplication from 45 to 39. This is not 45 factorial because we are missing times 31 times 37 all the way down to 1. However, this is a prime example of this case right here. So we have that this is 45 factorial, but now we have way too many terms. So we divide these extra terms away because we divide by 38 factorial. And this again becomes this multiplication right here. And we can rewrite this in an even nicer way because we can rewrite this as 45 factorial divided by 45 minus 7 factorial. And why would we write it like this? Well, because in this case we only have two numbers. We have this 45, which is the number of choices or the number of numbers that we have here. And we have this 7 right here, which is the number of terms that we have in this. And now we can simply calculate this to become a very, very large number. This becomes 228,713,284,800 possible combinations. However, this is not our final result, because at this point we did not incorporate the fact that the order of numbers that we choose does not matter. So whether this is a 2 on the first place and a 5 on the second place, or a 5 on the first place and a 2 on the second place, does not matter. The only thing that matters is that you picked A5 and A2. So let's see how we can modify this number of combinations to incorporate the fact that order doesn't matter. So let's now take a concrete example. Let's say that we pick the numbers 10, 11, 12, 13, 14, 15, and 16. These are 7 numbers that we picked, but whether we chose them in this order or any other order does not matter. So the question now becomes, in how many ways can we rearrange these 7 numbers? So again, we have 7 positions that we can occupy with any of these numbers. So in how many ways can we occupy these 7 positions with these 7 numbers that we picked? So let's, for instance, take this initial 10 here on the first position. However, it doesn't need to be on the first position. So how many choices of positions do we have for this number 10? Well, we see that we can put it anywhere on these 7 slots that we have. Let's put it, for example, here in this position. So we have 7 positions for this first number 10. Let's take the second number now, this 11. Also, this 11 does not need to be on this second position. So how many positions can we choose from to put this 11? Well, we again have these 7 positions. However, it cannot be placed on this middle position because the 10 is already there. This means that we only have 6 possible choices left. So let's say that we put this 11 on the final position. And we go on with this 12. We have, of course, 5 choices left. So let's take this 12 right here. The same goes for this 13, for which we have 4 choices left. Let's put it right here. For this 14, we have 3 choices left. Let's put it right here. This 15 can be put on either this position or this position. So we have 2 choices left. Let's put it right here. And for this last number 16, well, we only have 1 choice left, which is right here. So we only have 1 choice left. So again, to reiterate, as far as the lottery is concerned, this combination of these 7 numbers is equal to this combination of 7 numbers. And how many combinations are there for these 7 numbers to arrange along themselves? Well, exactly this number, this multiplication. Simply again, the multiplication of all of the number of choices for each number. And we see that we can write this in our new notation 7 factorial, because we multiply 7 with 6, with 5, all the way to 1. So let's now incorporate this in the formula that we had. We had that the number of combinations without thinking about order was 45 divided by 45 minus 7 factorial. But this was without taking into account that order doesn't matter. This means that in this total of choices, these 2 combinations were counted separately, so as 2 choices. However, we now know that since order does not matter, these should be counted as 1. And since there are 7 factorial number of combinations for each 7 numbers that we have picked, this means that for each 7 numbers that we have picked, we also counted 7 factorial other combinations that are actually the same. So we have to divide this number of combinations without taking into account that the order doesn't matter by this 7 factorial. And this gives us a grand total of possible combinations concerning the lottery of 45,379,620 possible combinations to pick 7 numbers out of a pool of 45 numbers. And if only one of these combinations is actually the winning number, then you realize that you have a tremendously small chance of winning the lottery. And this brings us to the end of this video, and I hope that you're now more familiar with how to solve these problems. If you have any questions, please leave a comment in the comment section down below. If you enjoy these videos, consider giving them a thumbs up. And if you want to get notified by future releases, you can always subscribe, of course. And with that, I thank you guys for watching, and I will see you guys in the next one. See ya.